One day, a lovely young lady asked me a question. Why is a conservative vector field always the gradient field of some real valued function? Well, let me think about that for a minute. Good question. Conservative vector field definition. A conservative vector field is often defined as a field that is the gradient of some real valued function called its potential function. That is, a conservative vector field f is the gradient of a real valued function, little f, which consists of the components, the partial derivatives with respect to x and y in 2 dimensions, or the partial derivatives with respect to x, y, and z if you're in 3 dimensions. So, my dear, it's defined, conservative vector fields are defined to be gradient fields. I guess what I really meant to ask was, why is it that only conservative, aka gradient, vector fields are independent of path? Well, independence of path, the definition, just to review for those of you who are watching, is the property that the work done in moving a particle between 2 points is independent of the path taken. Equivalently, if a particle travels in a closed loop, the net work done, the sum of the force acting along the path multiplied by the displacement, by a conservative force is 0. So, what is actually being asked by this beautiful young lady is that if the work done by a vector field along a curve from point A to point B yields the same value regardless of whether the curve is a straight line segment from A to B or any curved path from A to B, why is the field always a gradient that is a conservative field? In other words, why is the work done by the force along the curve when integrated equal to this function, some function f of b minus the same function at a for any curve from A to B, if and only if there exists a potential function, little f, such that that little potential function's gradient is in fact the vector field. So the vector field is related to a particular function called the potential function. And if that relationship exists, then to compute the work along the curve is simple. You just take the potential function at B and then subtract the potential function's value at A. Simple, simple, simple. But why is that so? First, let's look at an example from the real world, okay? For instance, gravity is a conservative vector field. If you climb up the mountain, I don't think I could do it, but if you did, go straight up, versus taking a nice winding path, the work done by gravity is going to be the same. Whether we climb straight up a cliff or take a winding path up that same mountain, the total work done by gravity on us is the same. That's a conservative vector field. Now, on the other hand, if you push a heavy box across a room, a straight line path will be less work than any winding route. You know, you could push it around and around the room for hours and then finally stop at point B. That's going to be a lot more work than if you just go straight from point A to point B, done. So that would not be a conservative vector field. You're working against friction, and friction is not conservative. Now, why are conservative, that is gradient fields, and independent of path fields equivalent? Well, let's take a look at it in 2D because it's kind of obvious when you do it just in 2 dimensions. You can see why it's true very quickly. Let's say f is a gradient field. Well, that means that f equals the components a comma b, where a is the partial derivative with respect to x and b is the partial derivative with respect to y of some function that we're calling the potential function. So if we integrate along the curve, the force times distance, we can rewrite that in a different notation as rewrite the vector field as f sub x comma f sub y, and then the change along the curve is just change in x comma change in y. So then when we dot those, we get the partial derivative with respect to x times dx plus the partial derivative of f with respect to y times dy. And now we're completely in terms of x and y at this point. We can change to t, where we're starting when t is equal to a and we're ending when t is equal to b. By a little trick, we just multiply by dt over dt, and that's just multiplying by 1, right? So take the denominator into the equation and leave the numerator out for your dt in your integral. Now look what you've got. That should look very familiar. What's in the little bracket there is the product rule. Yeah, it's the product rule. It's the derivative of what? Well, it's the derivative of f with respect to t using the product rule. So we can rewrite that integrand as the derivative of f with respect to t. And now we just have a simple integral that you did back in Calculus 1. And that's obviously f of a minus f of b. Ta-da! Now here's a picture of it. If it's a conservative vector field, and this one is a picture of a conservative vector field, which you will study about even more later, or maybe you already have. And so the work done in that vector field along the green path is the same as the work done along the blue path. Thank you. Oh, you're more than welcome, young lady. I hope that helps you understand why gradient fields, aka conservative fields, have that special property of being the gradient of a, when they have the property of being a gradient field, then they're going to be independent of path. And boy, are those easy to, those work integrals then are very easy to compute. You just use a potential function and subtract. Yay! Kind of similar to the fundamental theorem of calculus that you studied a long time ago. Bye-bye.